Good afternoon. My name is Katia Mocellin. I'm a full professor in CMEF, Center for Material Forming in France. It's my pleasure today to give this presentation dealing with numerical modeling of flow forming process. This work is part of the PhD of Ahmed Medioula. This work is performed in CMEF under the supervision of Pierre-Olivier Bouchard and myself. This is the outline of the presentation. I will first introduce the flow forming process and describe it. Then I will focus more on the computational time reduction method we have used. We will describe the results and we will draw some conclusion about this work. Here is our flow forming process. It is an incremental sheet forming process. Our sheet is an aluminum alloy sheet that is deformed between a mandrel and a roller. It is an incremental forming because of the local and repeated action of the tool. As you can see on this simulation, we have the contact area, and we can see that at a given time, this contact is really local and evolving all over the process. At the end of the process, the sheet has undergone a very large deformation that is difficult to reach, for example, with deep drawing. The final shape is a non-conical one, and there is a global thickness reduction all over the part and some inhomogeneous thickness all over the part also. This process is modeled by using the finite element software Forge. In this study, we are focusing on general results such as thickness reduction, for example, but also on local results such as strain and stress path and also damage evolution in the material. But we won't focus in this topic in this presentation. We have a very small contact area between the roller and the sheet, and the roller is evolving at a very high rotation speed. As a conclusion, we have to use very small calculation time step. The value is 10 to the power minus 4, and fine mesh size in order to describe accurately the thickness and the local values. We are naturally leading to accurate but very large CPU time simulation, but we are able to predict accurately the geometry and also the evolution of the local values. First hypothesis to reduce the CPU time is only to modify the kinematic of the process. In reality, we have the left configuration. The sheet is stuck between the tailstock and the mandrel, and the whole system is rotating. The roller is only moving in this XZ plane in order to define the sheet thickness reduction. In our simulation, we have changed the kinematic, and the sheet, mandrel, and tailstock are fixed, while the roller is rotating all over the system in order to describe exactly the same process. By using this simple modification, we are able to decrease by 10% the CPU time and also to handle more accurately the volume conservation of our piece. In order to reduce the CPU time, we also try to reduce the domain computation. Starting from the observation that the workpiece is almost axisymmetrical at the end of the process, and that at a given time of the process, the tool is only acting on the local part of the sheet, we try to reduce the domain. Here you can see some examples. To stabilize the problem, we had some symmetry planes, but those symmetry planes for sure add some edge effect, so we are only looking for the results on the median plane. So complete geometry on the left, and then 90 degrees, lower domains, up to 36-degree domain in order to reduce as much as possible the CPU time. If we decrease even more the domain size, we are leading to a computation problem because the edge effect of the symmetry planes are no more compatible with the material flow and the deformation due to the roller. So let's have a look now to these results. So on the left first, you can see that by doing such, we have the deformation of the sheet, but we can observe that most of the time of the simulation is performed while the roller is outside of the contact with the sheet. So it's a lot of CPU time, of useless CPU time. So we have identified and removed those calculation time step, and up to 80% of the calculation time step have been removed. At the end, we are only dealing with the time step that are of interest for the deformation of our sheet. By doing so, we are able to describe the deformation of the sheet, and we have reduced the CPU time up to 45 hours on 8 cores. So we have drastically decreased the CPU time. The CPU time is one thing. What about the accuracy? To do so, we will focus on the thickness distribution on the wall, that is this part, of our piece. Okay, we will plot the thickness here all over the z direction, that is -1. Okay, red point is the starting point for the measurement, and then we are comparing in black the reference case, that means the full case, and the 36-degree case in gray, and we can see that the results are quite similar. We have less than 3% of error in the thickness prediction. We are having a look also on the flow forming force, and again in black the reference case, and in gray the 36-degree case with the model reduction, and we can see that both the evolution shape and also the value of the force are quite identical for both simulations. That means that locally under the roller, the simulation is performing the same reaction. Now we focus on a more local study, and we have here some sensors that are put in the thickness of our sheet, and we will see that there is a roller side, a mandrel side, and a mid-thickness sensor. And we will follow the thermomechanical evolution in these three sensors during the flow-forming evolution. So first, let's have a look to the temperature versus time. So again, in black, the reference case, and in gray, the 36-degree reduced domain case. From the mandrel, from the mid-size, and from the other side, you can see that the temperature is a little bit different, but the difference is maximum 5% varying from the reference case. So we can conclude that at least the temperature is quite good. So the solution seems to be quite accurate on this case. What about another configuration? In this case, we change the process parameters of the flow forming. And what we can see is that obviously we have an excessive thinning of the plate here. What is plotted here, it's in green. It is the theoretical thickness, that means it is the distance between the mandrel and the roller path that is programmed. And in red, the thickness that is both measured and also predicted by our full domain approach. Again, the red curve has become black, and this is the theoretical thickness profile. So now let's try again to reduce our domain size in order to see if we are able to reproduce this black line. Here are the results. So the conclusion is that if we decrease the size of the domain for 120 degrees to 80, 60, 45 and 36, the results are getting worse because they are far away from the reality, but they are getting close to what is the theoretical thickness profile. That means that our reduced geometry is not able to predict the necking. At least it's not able to predict the material flow that is leading to the necking. So let's try to understand what is going on. So we will compare here the strain rate in two configurations. The green one is the first configuration where no necking was observed, and the red one is the one where the necking is observed. At a given time, we are plotting the value of the non-null strain rate during the process, this time of the process. What we can see is that with this configuration, we have a very local strain rate, non-null strain rate, and something that of small amplitude and symmetric with respect to the position of the roller. In the configuration where necking is appearing, you can see that we have a local position of the strain rate, a non-symmetric distribution of the strain rate on the domain, and also we have non-null strain rate all over the domain. That means that is a really 3D material flow that is going on in this configuration. So if you consider only one part here of your domain, you are not able to take into account this global material flow. And also, by taking into account two symmetry planes, it's quite difficult to handle the non-symmetric flow here all around the contact. So, for necking configuration, a more global material motion has to be taken into account. Another point is to consider a point that is located here in the median plane. So this is the initial position. It should be here in the full computation. And by considering this complete geometry, this point is moving here, we are looking from here, is moving out of the median plane during the process. With our approach with the reduction domain of 36 degrees, the symmetry planes are avoiding any displacement of this point, and it is stuck in the median plane. That means that this fully 3D simulation and this need of this material to flow outside of its original plane is not available with this kind of simulation. That means that the edge effects are too strong to be able to compute the real material flow that is going on. So the global material motion is more appreciated and more apprehended, better apprehended by the complete geometry. As a conclusion to this presentation, by considering the flow forming process, we have developed a numerical model that is giving very good geometric prediction, but with high computation time. So we have tried to optimize the configuration and to adapt the time step and to reduce the domain of our model in order to save time. What we can see is that on the first case, that is a problem without defect, we are able to reproduce global and local results with this reduced model. And also we have reduced drastically the CPU time. But by considering another configuration in which there is some necking phenomenon that is appearing, we can see that this necking, local necking, is in fact resulting for a fully 3D phenomenon, and we are not able to capture with this kind of domain reduction. So our approach cannot be used in any case in order to try to predict what is going on in the material during flow forming. I have now reached the end of my presentation. I can for sure answer questions in the chat of the conference, and if you want also to ask some questions you can use also those two emails in order to get some answers. Thank you.